dear students. So, in this class we will try to address atmospheric dynamics. So, what do I mean by studying atmospheric dynamics? So, we have to understand the atmosphere of the earth is a fluid which is moving from one point to another point continuously. Right. So, why does it move or how does it move, and why do we have to understand these motions from one point to another point is going to be the topic of discussion for today. So, basically we have to understand the movement of atmospheric fluid. So, why does it move? What a direct consequence of this movement is that we see all the weather and climate, short scale or long scale. The direct consequence of this movement is that you see weather and climate. If you see the earth, you will notice that there are several circulation patterns, but the most important, if you consider the one cell circulation of the atmosphere of the earth, you will realize that the air has to rise from the equator, because equator is where the temperature is maximum or more amount of heat is received. So, it forms. So, this is the one cell circulation model. So, air rises, the density becomes very low here. It kind of goes towards the colder regions where density becomes much larger. It sinks towards the surface, and then in order to replace the air that is rising away from the surface, it moves towards the equator. Right. This is a simple one cell circulation pattern, but the point is we have to understand why does the air move from one point to another point and create weather or climate. Right. So, in order to do that, we have to consider the entire atmosphere as a fluid element. So, we cannot treat it as anything else, but when you treat it as a fluid, you have to understand what type of loss this fluid can be subjected to. What type of loss of physics, let us say loss of thermodynamics or loss of mechanics, can we apply on this fluid and get a accurate behavior, get to understand the behavior of the fluid. Right. Now, when you talk about fluid, there is no end to it, right. So, in order to minimize the thing, what we do is we will consider a very small volume of air, which is an actual representation of the atmosphere. That means it has the same constituents as that of the atmosphere, but this is an actual representation. But this is the smallest possible element, which also represents the state of atmosphere. What we do is we will try to apply the laws of physics on this volume of air, and then let us say if this is subjected to such type of forces, how will this parcel of air or the fluid element will move from one point to another point. And if it moves, its position has to be written in terms of x, y, z and t. And if you are able to understand, if your description is complete, then it means how the x, y, z change with respect to the time will tell you the accurate behavior of the volume of the air. So, you call this volume of the air as the control volume, or you can also call it as the air parcel. Right. Now, the point is you have to see how you can get these x of t, y of t and z of t. What do they tell you? They tell you how the air parcel is going to behave, where it is going to go, and which trajectory it is going to take from one point to another point. Essentially, we are trying to understand the atmospheric motions. That is it, as simple as that. Okay. Right. Now, let us say, so when something is moving, how do you describe it? What is the reason for it to move? The simplest answer is a force has to be responsible for an object or anything to move from one point to another point. Right. Now, what are the forces which are relevant for motions in atmosphere. Let us say for what are the fundamental forces which are relevant for the motion in atmosphere. So, you can think of many forces. When I talk about force, when I talk about a force, it can be inertial force or non-inertial force. Within inertial force, there are many different types of inertial forces, and within non-inertial force, there are many different types of non-inertial forces. But listen to this very carefully. When an object is moving from one point to another point, a force has to be responsible for its motion. And the way the object moves, the velocity with which the object moves, or the acceleration with which the object moves, every parameter related to the motion of the object from one point to another point has to be decided only by the amount of force and by the nature of force that is acting on it. So, having said that, so what are the forces which are relevant in atmospheric physics? Whenever you talk about fluid, you are trying to combine two things basically. You are trying to understand how the laws of thermodynamics come into picture, and then how the laws of fluid mechanics. So, how the laws of fluid mechanics will come into picture. This is what you have to understand, right. Now, all these we will try in the course of time, we will try to derive all these laws of thermodynamics which are relevant, and all the laws of fluid mechanics which are relevant for understanding the motion of fluid from one point to another point. Very well, right. Now, let us talk about forces. What is a force? Force is something which moves an object from one point to another point, right. And what are the forces which are relevant for describing motion in atmosphere? So, if you look at the force, basic nature of force, it can be basically characterized into two different types. One type is the real force, the second type is apparent. There are real forces and there are apparent forces. What are real forces? Real forces are the ones which make the body move in a particular way or in a particular direction. Apparent forces are the ones which are basically inertial reaction terms for the real forces. We will come back to that. But when you talk about the nature of the brief types of forces which are responsible for moving the atmosphere from one point to another point, these forces are basically they can be classified into two different types. One type of force are called as surface forces, and another type of forces are called as the body forces. The surface forces are the ones which will act across the surface of an object. They do not depend, they are not dependent on the mass, rather they do not act towards the center of mass of an object on which the force is acting. The body forces, on the other hand, the magnitude of the force that is acting on an object seems to be proportional to the mass, or they will act towards the center of mass. So, body forces will act towards the center of mass, and surface forces will they are not pinpointed, they do not point to a particular point, rather they act across the surface, right. So, the easiest examples for surface force are the friction. Friction is the most readily available reference for surface force, and for a body force the most easily imaginable force is the gravity, right. Now, what I am going to do now is I am going to write the names of those forces which are relevant for moving the atmosphere from one point to another point, right. These forces are basically, let us say they are, what are the forces? One, the most important force is called as the pressure gradient force, which is also called as the PGF. Then we have gravity. Then you have the frictional force. Then you have the Coriolis force. Then we have the centrifugal force, that is it. So, these three forces are real and these two forces are apparent, right. So, these three forces can also be called as the inertial forces, and these three forces are non-inertial forces, as simple as that, right. Now, most importantly, all these forces in their complete description or the mathematical derivation for these forces was actually addressed in the earlier course, which is the Introduction to Atmospheric and Space Sciences. So, you can refer to those videos in order to be able to understand the true nature of these forces, how they act and how to be able to derive an expression for these forces per unit mass. Right. So, in order to avoid repetition, I am not going to the details of deriving all these forces. You can simply refer to those videos. Right. So, what I am going to do now is I am going to write directly how we can write an expression for force per unit mass of these forces. So, ultimately the idea is, what is the idea? The idea here is to be able to write this expression m dv by dt is equals to sum of forces. What is this? This is an equation of motion. So, how the acceleration of the object, see this is basically dv by dt. If you integrate it once, you will get velocity. If you integrate it twice, you will get position with respect to time, right. So, this is the equation of motion. It tells you how position is changing with respect to time. The rate at which the velocity changes is equal to the sum of forces per unit mass, right. Now, we have how many forces we have? So, this has to be sum of F1 plus F2 plus F3 plus F4 plus F5. So, this is this going to be plus or minus or whatever it is. So, basically we are just trying to see how these 5 forces can be added to be able to write an equation of motion. What is the role of equation of motion? Equation of motion tells you accurately how the motion is taking place, how things will move around, right. Now, we will go, what I will do is I will not do the derivation of these forces, I will just try to see how the equations, how these forces can be defined. So, the first comes the first one is the pressure gradient force. This force is by far the most important force when you talk about atmospheric dynamics. So, this force is called as the PGF, pressure gradient force. So, pressure gradient force per unit mass is written as force per unit mass, which is acceleration, is written as minus 1 by rho del P. Right. Most importantly, I will tell you the most important characteristic or the important aspect of this force. The pressure gradient force, how does it act? If you imagine a fluid, let us say if there is a low pressure here and if there is a high pressure here. You very well know that diffusion is something which comes into existence now, and there will be fluid motion from high pressure to low pressure. Why is this motion happening? This motion is just happening to equate the pressure or to maintain a uniform pressure level throughout the volume, right. So, this is the basic nature of force. The force which is driving this diffusion from high pressure to low pressure is called as the pressure gradient force. Now, interestingly, the magnitude of this force will not really depend on the pressure itself, rather the magnitude of this force will depend on the gradient of the pressure or the difference of the pressure. And since you have a minus, the direction of pressure is always opposite to the gradient. So, if you see in this picture, the gradient is in this direction. Gradient always points in the increasing direction of a physical quantity, right. But the force is actually acting in the opposite direction. So, this is the minus that symbolizes this opposite directions of the gradient and the actual force. So, one important aspect is the pressure gradient force won't really depend on the pressure, rather it would depend on the gradient of the pressure. The second important aspect is the force will always be opposite to the gradient, right. So, pressure gradient force is by far the most important force which drives the global circulation, or which drives the air movement from one point to the other point. This force is of course complemented sometimes by other forces, or sometimes countered by some other forces. And how this counterbalance will work out will actually decide how the wind will move from one point to another point. Right. So, now let us say the second type of force is the gravitational force. This is simply the gravity. So, you write F as minus g mm by r square with r cap. Right. So, here the important thing is this force per unit mass is simply minus gm, or A, the acceleration due to gravity, is gm by r square r cap. Right. Now, if this is at the surface, then you write, so we write it as g star is equals to minus gm by r square r cap. What does it mean? It means this is the gravity at the surface, right. Now, when you take it to a height, now here the entire mass, so this is a point force, this force acts from a point between 2 points, right. This is a point force. Now, what you do is you take capital M to be the mass of the earth and small m to be the mass of the entire atmosphere itself. And if you take it from the surface to a particular point, you have to write it as gm by r plus h whole square r cap. What does it mean? It means that you are trying to write how the force will act at a height away from the surface, right. Now, here most importantly you will have to see whether g star will vary much with respect to height or not. So, every time when you are trying to write the force, should you take the universal, should you take the g as 10 or 9.8, or should you also account into the variation of g with respect to height? The answer is, we know very well from our understanding of the basic aspects of the Earth's atmosphere, we know very well that the 99.9% of the mass of atmosphere is well within 50 kilometers starting from the surface. You know that very well, right. So, what does it mean? So, it means that this 50 kilometers is nothing in comparison to the radius of the earth, which is 6,400 kilometers. So, if you add or subtract this small number h from this, it will not really matter. So, for calculations in atmosphere, in the Earth's atmosphere, dealing with the Earth's atmosphere, the top height of the atmosphere, you do not have to bother the variation of gravity with respect to height, as long as you are talking about the Earth's atmosphere. If you go far beyond, if you are, let us say if you are trying to calculate the orbital velocity of a satellite or anything like that, then this particular value becomes even more relevant. This particular h that you add in the denominator becomes even more relevant, right. So, this is the force, the pressure gradient force per unit mass, and this is the gravitational force per unit mass. Then you have the frictional force or the viscous force. So, what is viscous force? What is the nature of viscous force? Viscous force comes into existence whenever there is a fluid, or when it exists between two successive layers of a fluid. It gives the fundamental property to the fluid not to move, or it gives the fundamental property of resisting the motion for a fluid. So, fluid layers sitting on the top of each other will exert forces so that it resists movement from within the fluid, right. So, viscous force is an analogous force to the friction. If you are talking about solid objects, you say it as friction, and if you are talking about fluids, you say it as the viscous force. Right. So, there is a detailed derivation for viscous force in earlier videos. So, where we take a fluid and we try to displace the top layer so that it achieves a constant velocity of v, and it so happens due to the viscous force, the amount of force that you applied on the top kind of gets very small to the bottom due to the friction itself, and you will see that the velocity at the bottom of the fluid becomes eventually 0. So, how this velocity drops, or what is the reason? How does the molecular molecular motion or momentum transport from the bottom unequals the momentum transfer from the top? How these things can be mathematically derived can be referred to the earlier videos. But if you write a similar expression, let us say A, which is force per unit mass, let us say along z, along the fluid is along z direction, and the movement is trying to be along the x axis. So, it can be written as dou tau zx divided by dou z, right. So, now what I will do is, for reference I am not going to derive the entire expression, I will simply write those values, those different values of stress tensor. A x x is 1 by rho dou tau x x by dou x along y direction, A x y and along the z direction right. So, these are the values of so now we can combine all this and we write A x is nu del square u, A y is nu del square v, A z is nu del square w, or where nu is the kinematic viscosity coefficient, which can be written as mu by rho. What is mu? Mu is the dynamic viscosity coefficient, right. So, now we can combine these three. Let's talk about the non-inertial forces later. For inertial forces, we can write dV by dt is minus 1 by rho del p. So, I am writing this as per unit mass plus nu del square u. So, this is the equation of motion as long as you are talking about the inertial forces, the rate at which the acceleration per unit mass is going to be written as. So, what is this? This is the pressure gradient force, this is the gravity force, and this is the viscous force, right. Now, this is so in atmosphere these are the only forces which are relevant. Let us say what other force comes to your mind? Electromagnetic force, it is not relevant in atmosphere. In macroscopic scale, it is not relevant. So, the acceleration per unit mass will depend on the interplay between these three forces. How the gravity is more, how it counters the pressure gradient, and how does the viscous force alters this balance of gravity and pressure gradient. For example, the simplest example is if you consider the earth. So, you have when you see the pressure rho or the density, it varies like this, right. So, what does it mean? There is a exponential decrease of pressure from the surface, but what really happens is there is a high pressure near the surface and there is a low pressure away from the surface. So, since there is a difference of pressures, there is a pressure gradient. The pressure gradient is in this direction, and ideally the fluid motion should be in this direction. So, naturally all the fluid should escape the planet, and the atmosphere will have to cease to exist, but it won't happen like that. What generally happens, this escape is exactly balanced by the gravity. So, that means this motion, this vertical motion of the atmosphere is not possible by itself, because this velocity. So, dw by dt is 0 basically. Why? Because gravity exactly equals 1 by rho del p. So, that is why. So, there is no vertical escape of the atmosphere, right. Now, this was about the inertial forces. Now, let us talk about the non-inertial forces. So, there are basically two important non-inertial forces which are responsible for movement. So, what are they? Non-inertial forces. What is a non-inertial force? So, generally speaking, we define the motion of atmosphere in a geocentric frame of reference. What is a geocentric frame of reference? A geocentric frame of reference is the one which is fixed with respect to the earth. So, as long as it is fixed with respect to earth, it is inertial. When it is inertial, anything which is moving at a constant velocity with respect to that frame is also inertial. So, as long as you are talking in inertial frame of reference, these three forces are enough to describe. But what happens is, if you go away, what you will realize is that the geocentric frame of reference that you are talking about is of course fixed to the earth, but the earth itself is not at rest. It is moving with respect to itself. Earth is moving with respect to so many other things. Earth is moving around itself. So, it constitutes a frame of reference which is called as a rotating frame of reference, or more precisely a non-inertial frame of reference. So, when there is a rotation, when there is an acceleration involved, what will happen is there will be reaction terms to the inertial forces. Or a simple example, a simple thought experiment is that if you consider an object tied to the end of the rope, and if you are rotating it like this, so what you will see is that there is a force which is acting on the. So, if this is the object, let us say this is the object, this is where you are holding it and you are rotating it. Right. Now, there is a force, of course, which is rotating the object. Now, as long as you see from here, from the point of your reference, you will see that this force, what is the role of this force? This force is moving the object in a circle, right. It is attributing a velocity to this object. But imagine yourself on this object which is moving. So, if you are on the top of that object, you will realize that you are at rest, but then you will see a constant non-zero force which is acting on the object. So, you will have to wonder that there is a force which I am able to see, but this force is not able to move me. So, why is that? So, then the obvious answer for this is there is additional force. You will have to explain, you will have to think there is additional force which is a reaction force to this F, and then you will see that this reaction force is nullifying the effect of this force, so that eventually or at the end this object is at rest. So, these are the reaction terms to the inertial forces. So, two very important in non-inertial forces which contribute to motion of atmosphere from one point to another point are the Coriolis force second is the centrifugal force. So, like I said, I will not go into the derivation of these forces, I will use the expressions directly. Okay. So, Coriolis force is 2 omega cross V, and the centrifugal force is minus omega square r, right. Now, so this is now if we can write the full equation of motion, which is dV over dt is equals to minus 1 by rho del p plus g star plus eta del square u minus 2 omega cross velocity plus omega square r. So, this is the full equation of motion. Okay. So, you know what is what now, right. So, now this is the equation which will tell you how the air will move from one point to another point. So, here at this point of time what I have to tell you is, so here the velocity, this is the acceleration, or which is the force per unit mass. All other forces are indeed force per unit masses. So, this equation is called as, this equation is what is this equation? This equation came out by conserving what? Conserving force, right? Conserving force. So, this equation is called as the momentum equation. Momentum equation. So, we will stop here. So, this is the conclusion is that we have been able to see how the atmosphere moves from one point to another point, and what are the contributing factors to understand this motion, what are the contributing factors which will cause this motion. So, these 5 forces are the most important ones which will make atmosphere move from one point to another point. So, in the next class we will try to see how exactly we can combine the gravity and the centrifugal force, and what is the consequence of such a combination and things like that. Okay.